Alright, so here is the next video on the What the Hectogon channel. What the heck?
Hectogon.
It's finally getting cold enough for me to wear one of my favorite shirts. This fantastic Elon Musk smoking a joint on Joe Rogan's podcast, blowing the smoke into space. And as you can see, it becomes the car that this mofo launched into space. Pretty amazing. Pretty amazing. I saw this online on like some Instagram ad, probably almost a year ago now, and I was like, name your price, I'll f***ing take that shirt. But, point is, I just wanted to show this shirt off eventually. It's very nice. So today we're going to be covering a very, very interesting topic that's just fun to sort of manipulate and go along with. We're going to be taking a look at the gamma function. Very, very nice function. The analytic continuation of the factorial function to numbers other than positive whole numbers. And what we're going to be doing is in this video establishing two things. We're going to be taking a look at the beta function, which is a very interesting integral and can be written in terms of the beta function with two different inputs, two different variable inputs. So the beta function is a function of two variables. And from those two facts, we're going to be able to derive Legendre's duplication formula, which is a way of expressing the gamma function of 2 times a quantity in terms of other forms of the gamma function. So it's sort of, I wouldn't call it a functional relationship. Maybe it is. Maybe that's what that's called. But it's a nice way of writing that, and that will allow us to manipulate the answer that we get in the next video that I'm going to make here, which will be another wacky integral video involving powers of the sine function instead of powers of the tangent function. So, let's get into it. I'm going to be referencing, not directly referencing this book, but some of the proof, some of the stuff that I'm going to be doing is informed by this book and the Wikipedia pages for the gamma and beta functions. Also, I just want to highlight, I've gone through the Little Gamma book, the gamma constant as opposed to the gamma function, by Havel again, and I've notated, to the chagrin of probably many, many book lovers with tons and tons of doggy ears in the book, all the places where I found interesting math that I want to make videos for on this channel, and I'm super, super excited about going through this book because this is a great, great book. So, very excited about this. This will be for another gamma time. Right now, it's big gamma time. Okay, so today we're going to be investigating these two very interesting functions. We have the gamma function of z, which if z is in fact a positive whole number, one of the natural numbers, then it is equivalent to z minus 1 factorial. And you can sort of test that by doing integration by parts on this integral, and you see that you do in fact get the functional relationship that the factorial function has if only shifted over by 1. So this is the definition of the gamma function. It's the integral from 0 to infinity of t to the power of z minus 1, this z right here, times e to the negative t dt. So the area under this curve, with t as the variable, is equal to the gamma function. And we have this rather strange definition over here, that capital beta, not b, capital beta, of x comma y is equal to gamma of x times gamma of y over gamma of x plus y. And this may seem like a strange thing to formulate as a quantity, but when we investigate how we actually get to this by considering the product of the top two gammas, you'll see that this falls right out of the math, and we'll end up with a very, very interesting relationship with regards to what exactly the beta function equals. And it's a very, very nice integral in the end. And we're going to reveal a couple more ways of writing it, one of which I've already used before in a previous video involving trigonometric functions, so we'll just cover those as well in the video. And as a result of being able to derive what the beta function actually is as an integral, we can then find out Legendre's duplication formula for gamma of 2z. So, assuming that we know this already, and that this is our goal, let's figure out how we can derive this. So the first step is to consider the product of the gamma function. So we'll do gamma of x times gamma of y, which by just simply using the definition of what the gamma function is going to be integral from 0 to infinity, r to the power of x minus 1 times e to the negative r dr times the integral from 0 to infinity of s to the y minus 1 times e to the negative s ds. And now, because this is entirely in terms of r and this is entirely in terms of s with regards to their variables, we can just combine these two using, I believe isn't that Fubini? Fubini's theorem? Papa Fubini? Insert Fubini-roid right on the screen, but I wouldn't steal that from Papa Flammy, of course. We can just combine these into one integral. or I'm sorry, one double integral. So this is going to be equal to the integral from 0 to infinity of the integral from 0 to infinity of r to the x minus 1 times s to the y minus 1 times e to the negative r minus s, right? Because if they have the same base, we can combine them by simply adding the exponents. So we get e to the minus r minus s and dr ds, right? So now we've got this fanciful double integral, and all we're going to do is make a substitution. Now this may seem like a slightly odd substitution, and we'll need to calculate the Jacobian matrix, the absolute value of the determinant of the Jacobian matrix, to figure out what the new, whatever this thing is called, you know what I'm saying. Can't remember the word for some reason. So what we're going to do is our substitution is going to be r is going to be equal to u times t, and s is going to be equal to u times 1 minus t. So both of these separate variables are going to be in terms of the same two variables. So what we need to do is we need to be especially careful here, because we need to now consider what our, much like when you convert into polar coordinates, you have your x and y being put in terms of r and theta, you then have to consider the Jacobian matrix. We have to do the same thing here. So the Jacobian matrix, you take this object, the substitution for r, and take the partial derivative with respect to the first thing. So we're going to do, essentially it's going to be partial r with respect to u, and this one's going to be partial s with respect to t, and this one's going to be partial r with respect to t, and this one's going to be partial s with respect to u, right? I think so. And what we're doing is we're taking the determinant of this matrix, of this matrix of derivatives. So we're going to get t, 1 minus t, u, and negative u. And this should work out, right? So what we're going to end up with now, we just simply take the determinant now. So it's the product of those two things, negative u times t, and remember we're taking the absolute value, minus the product of these two things. So minus u plus ut. And this comes out to be the absolute value of negative u, which is of course equal to u. So what we know now is, given these substitutions, the differentials at the end of the integral, when we make these substitutions, is now going to be u times du dt. So this is what this is what determines what is being multiplied by what you replace these with. Because if we just have dr ds and we make these substitutions, we end up with du dt, but then we have to multiply by this. This is what the absolute value of the determinant of the Jacobian matrix is for. And whenever you do a u substitution in, say, a single integral, the u substitution is the determinant of the 1 by 1 Jacobian matrix, which is of course just the term in the matrix. So it actually generalizes to the even simplest case. So in this instance, we know exactly what we need to replace all of our things with now. So I'm going to erase this. We know that we're going to have u times the du and dt at the end. Okay, so let's do that. So we've derived the determinant of the Jacobian matrix now. And so with these substitutions, what we're going to have is we're going to go from u equals 0 to infinity, and from t equals 0 to 1, and I'll explain that when I'm done making all of the substitutions. And we're going to replace r with ut, so we have ut to the power of x minus 1. And we're going to replace s with u times 1 minus t, so we have u times 1 minus t, all to the power of y minus 1. And if we now combine r and s, so r plus s, we end up with ut plus u minus ut, which means that r plus s is equal to u, right? Which is what we need, because what is this? This is e to the minus r minus s, which is the negative of the sum of r plus s. So it comes out to, when we do the substitution, we get e to the negative u. E to the negative u. And we end up with the factor of u from solving for the Jacobian matrix, dt du, right? So this is the substitution we have to make for this, because we solved the Jacobian matrix. The reason we want u to go from 0 to infinity is so that both r and s go from 0 to infinity just like they do. The reason we picked t to go from 0 to 1 is only because we have t here and 1 minus t here, so that the values go from 0 to 1 here as well as here, and u is allowed to go from 0 to infinity, thus ensuring that r and s both go to infinity. Had we gone from t equals 0 to 2, I would have had to do t and 2 minus t, and we would have been able to sort of shake the integral a bit, shake out the things that we need to, and we would probably end up with the same answer in the end. But for the most convenience, you'll find that it actually makes the most sense to just pick 1 minus t to go here, which means for the sake of making sure that r and s both do still go from 0 to infinity, we just need to go from 0 to 1 with t. Okay? Again, had I picked this to be any number here, I would have just had to change that number here to that thing. And the thing that we want would have fallen out of the integral in the end. This is just picking the most convenient values. I hope that's clear to everybody why those bounds have been picked. So now I'm going to do separation of variables, because you'll find that everything involving u and t are strictly separate from each other in their products. So I'm going to take all the u stuff and bring it out to the front. So we have the integral from 0 to infinity of u to the x minus 1 times u to the y minus 1 times e to the negative u times u du. So that's all the u stuff taken out. And now the integral involving only stuff with t goes from 0 to 1, and it's t to the x minus 1 times 1 minus t quantity to the power of y minus 1, so 1 minus t to the power of y minus 1 dt. And now we can do some simplifications, because we can include u here. So we have u to the x minus 1 plus y minus 1 plus 1, right? So in total, if you add x minus 1 plus y minus 1 plus 1, you end up with the integral from 0 to infinity of u to the x plus y minus 1 times e to the negative u du times the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt. But what is this? This is very clearly, according to our original definition of the gamma function, this is the gamma function evaluated at x plus y. So what we've just determined is that gamma of x times gamma of y is equal to gamma of x plus y times something. But since we already defined the beta function previously to be this product divided by this, which is gamma of x plus y, if we just divide this on both sides and end up with this divided by this, we end up with just this integral, which means that this integral has to be equal to the beta function that we derived before. So what we can do is divide both sides of the equation by this, and we'll have a formula for the beta function. So I'm going to erase all this now that the proof is done. So what we've just derived is that this product of things is equal to gamma of x plus y times the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt, which if we divide both sides by this, we end up with this fact, which is exactly the definition of the beta function that we had before, which means this integral is the beta function, the function of two variables, right? So this is the beta function, the integral from 0 to 1 of t to the x minus 1 times the quantity 1 minus t to the power of y minus 1 dt. So this is what we wanted to derive. We have this cool little fact. So now we know the beta function is equal to this, and we're going to do a couple of substitutions to derive other forms that we've found useful. So I'm not going to derive the one that we used in the powers of tangent function, because Papa Flammy already did a video on that, and I'll link to it right there. Right there. Right there. You can see how we would easily get to the one with trigonometry, because if we let t be sine squared and therefore 1 minus t would become cosine squared, you can see where that would come from. So that's very easy to derive, just a substitution. So we're going to make a slight substitution that we need for when we derive the Legendre duplication formula. So we're going to let t become t squared, which means that dt is going to become 2t dt. And for this to go from 0 to 1, much like t, we just need the integral to also go from 0 to 1. So we're going to bring this factor of 2 out to the front. It's still going to go from 0 to 1, and we're going to have t, and I can multiply these powers together, so we're going to get t to the 2x minus 2 times 1 minus t squared to the y minus 1 times t dt, because the factor of 2 is out here at the front, this factor of 2 right here. And because this is a power of t, t to the power 1, and this is a power of t, we can just combine those. So we get that the beta function is also equal to 2 times the integral from 0 to 1 of t to the 2x minus 1 times 1 minus t squared to the y minus 1 dt. And so this is another version of the beta function that we're going to need when we finally derive Legendre's duplication formula. Okay, so let's actually tackle that now. So we have these representations of the beta function. We also have the definition of it, which is gamma of x times gamma of y over gamma of x plus y. And we have the version that we've used before, which is 2 times the integral from 0 to pi over 2 of sine of theta to the power of 2x minus 1 times cosine of theta to the power of 2y minus 1 d theta. Right? So we have these 4 representations. This one I've proven today. This one, using the definition of the gamma function, this was the definition that we used to sort of see what our goal was. This I just proved now by making a simple substitution, and this one Papa Flammy proved in one of his videos, which I did utilize while doing the powers of the tangent function integrals. So what we're going to do now is try to derive what could gamma of 2 times z be equal to. So naturally a nice place to start would be to utilize the beta function by simply considering beta of z comma z. So the same input for both variables, which means by the definition of the beta function we have gamma of z times gamma of z divided by gamma of 2z. So there's the start that we want to sort of have, right? And we can sort of start from the definition of the original version of the gamma function just by plugging in the values z and z for the variables, right? So this is the integral from 0 to 1 of t to the z minus 1 times 1 minus t to the z minus 1 times dt, right? Very simple. So theoretically we could combine those, but that's not what we're going to do. We're going to make the substitution of t equals 1 plus u over 2, which tells us that dt has to become 1/2 times du, doing a simple derivative. And so that the integral is equal, we need to make sure that if t is equal to 0, then u has to be negative 1, because 1 minus 1 is 0, 0 divided by 2 is 0, and if we want t to be 1, we know that u has to be 1, because 1 plus 1 is 2, and 2 divided by 2 is 1. So the new integral is going to have a factor of 1/2 on the outside, and it's going to go from negative 1 to 1. And so now we can make our simple substitutions. We're going to have 1 plus u over 2 to the power of z minus 1, times 1 minus 1 plus u over 2 to the power of z minus 1 times dt. And remember that factor of 1/2 has been brought to the outside of the integral. Now what we can do is combine these. 1 is the same as 2 over 2, so what we can do is simplify this as 1/2 times the integral from negative 1 to 1 of 1 plus u over 2 to the power of z minus 1 times 1 minus u over 2 to the power of z minus 1 dt, right? Because when we do 2 over 2 minus 1 plus u over 2, we end up with 1 minus u over 2. Just combining those two terms together, we end up with that right there. But now what we can do is tally up all of the powers of 2 that we have. We have 2 to the negative 1 out here, and we have 2 to the 1 minus z and 2 to the 1 minus z. All I did was reciprocate and make it negative. So what we end up with is 2 to the negative 1 times 2 to the 1 minus z here, times 2 to the 1 minus z here, on the outside of this integral, which goes from negative 1 to 1, and we're left with 1 plus u to the z minus 1 times 1 minus u to the z minus 1 dt. Right, now we can combine all of these together and sort of combine those as a difference of squares in a sense, right? So we have negative 1 plus 1 minus z plus 1 minus z as the powers of 2. So if you combine those together, you end up with 2 to the power of 1 minus 2 times z times the integral from negative 1 to 1 of what is 1 plus u times 1 minus u? It's 1 minus u squared, right, to the power of z minus 1 dt. Look at this. We have a symmetric integral, right? It goes from negative 1 to 1. But if you take a look at 1 minus u squared to the power of z minus 1, if we were to plug negative u in, the square is going to make that irrelevant, which means that this function is an even function. So if we're taking the integral from negative 1 to 1 of an even function, it is simply 2 times the integral from 0 to 1 of that function. So we can rewrite this as 2 to the power of 1 minus 2z, which is that constant that we have at the front, which we got from all of these powers of 1/2, right? Just trying to keep track of everything, times 2 times the integral from 0 to 1 now instead of negative 1 to 1 of 1 minus u squared to the power of z minus 1 d. Sorry, I forgot to make that. Whoops, look at that. Silly me. All of those should have been du's. Sorry about that. Du and du. So what we're going to do now is we're going to set the thing that we plugged in, so we get 2z right here. We're going to set this thing equal to what we just derived that it's equal to, this thing right here. So I'm going to erase everything in between, all the steps, and we're going to just set it equal to this. We know now that this is equal to 2 to the 1 minus 2z times 2 times the integral from 0 to 1 of 1 minus u squared to the power of z minus 1 du. Right? That's what we know that this is equal to, just from that whole process that we just derived. But we also derived that from before, that beta of xy, x comma y, is equal to 2 times the integral from 0 to 1 of t to the 2x minus 1 times 1 minus t squared to the y minus 1 dt, right? And so if we just consider u to be our variable, right? Clearly there's no u to the 2 times something minus 1, right? Which means this term in this integral has to have a power of 0. And to make 2x minus 1 0, x has to be 1/2, right? Because 2 times 1/2 is 1, and 1 minus 1 is 0. So that would make this term go away. And then look at that. This is just this term with z as the input instead of y. So this whole thing is beta of 1/2 comma z. And that's sort of the crux of this that we're able to prove. So now we can set this equal to this, and we can finally isolate gamma of 2z. So what we can now say, based on this thing that we discovered before, that gamma of z times gamma of z over gamma of 2z, which is by definition beta of z comma z, is equal to 2 to the 1 minus 2z times beta of 1/2 comma z. But what is beta of 1/2 comma z? Well, we can just use the definition of the beta function to rewrite that as 2 to the 1 minus 2z times gamma of 1/2 times gamma of z divided by gamma of 1/2 plus z. And now all we have to do is solve for gamma of 2z. So on both sides of the equation we see that we have a gamma of z, so we can cancel that, right? Gamma of 1/2 is simply the square root of pi. That's a pretty easily derivable fact. You can actually use the beta function to derive that fact by doing beta of 1/2 comma 1/2, because in the bottom you'll get gamma of 1, which is just 1, and you'll get gamma of 1/2 squared, and then when you plug that into the original definition of the gamma function, you see that that evaluates to the area under the Gaussian integral, which is pi, and then you take the square root and you get that it's the square root of pi. So it's pretty easily derivable. So this is actually equal to the square root of pi, right? And now we can isolate gamma of 2z. So we multiply that over, multiply those things over, rearrange the equation, and we end up with the fact that gamma of 2 times z is equal to, since we have to multiply that over to the other side, we get 2 to the 2z minus 1 times this single gamma function, so gamma of z, times gamma of z plus 1/2 times pi to the negative 1/2, because we'll be dividing that over, so we get pi to the negative 1/2, or 1 over the square root of pi. So we've now derived Legendre's duplication formula. So in this video, we've both proven the relationship that gamma has to the beta function, and we've been able to show how you can write gamma of 2 times a number, and that is equal to 2 to the power of 2 times the number minus 1, times gamma of that number, times gamma of that number plus 1/2, times 1 over the square root of pi. So very, very beautiful formula. I hope that wasn't too quick. I just kind of wanted to get this part done so that we can use this fact and the beta function to evaluate what I want to do in the next video, which is the next installment of the Wacky Integrals videos, where we will be investigating this function, s of x equals the integral from 0 to pi of sine of t to the power of x dt. So whatever this equals, we're going to need the gamma function and the beta function and Legendre's duplication formula to do some kind of fun manipulations of it, but we're going to see this in the next video. And that's after we've derived these facts, which we have now. So thank you for watching. I'll see you in the next video, and it's time for... I have an Instagram page for the channel. It is at @WhatTheHectogon, of course, spelled correctly, unlike my email, right? Hectogon, I spelled in the email with an A here, when in fact it's an O. WhatTheHectogon on Instagram, so this is Instagram. I post channel updates there. I also am doing a lot more reading than I used to now, so I'm posting books that I'm reading that I recommend to people. I have a collection of vinyl records that I like to share. Follow me at @WhatTheHectogon on Instagram. I'd like to point out that one of my best friends, who is very much into Dungeons & Dragons, has a YouTube channel called Marching West. He does like a little podcast about Dungeons & Dragons. He does Dungeons & Dragons all the time through his Discord server. He's very, very into it, and I'm sure he would appreciate a bit of a mention. So if you're into Dungeons & Dragons, visit his YouTube channel, Marching West. He also has an Instagram account, again, at Marching West. Also, this fellow, Bill, and I are starting another YouTube channel. I guess you could call it personal reasons, even though it's just kind of funny, is called Fredwood Live. On YouTube, we're just called Fredwood. It's an amalgamation of two different things that were sort of important to us in our college days, which are getting farther and farther behind us. So this is, again, YouTube. We have a channel called Fredwood. We're going to do kind of silly, just us riffing off of each other vlogs that we edit together in humorous ways. But we're also going to start doing weekly video game streams on Mixer. And on Mixer, our name is Fredwood Live. So if you want to see two kind of dopey former college students do kind of ridiculous video game streams and also other things that we're going to do on top of that on Mixer, our username is Fredwood Live, so check us out. Likewise, we have a Twitter account to promote it, also at Fredwood Live. So I apologize for all of these different promotions. I figured I'd just start putting these out there. So there's a few that I'd like you to check out if you're interested. Is my Instagram account, What the Hectogon. On YouTube, my buddy Bill's channel, Marching West. It has to do with podcasts and the like relating to Dungeons & Dragons. The Instagram account for channel updates for that channel. Our joint channel, Fredwood, where we're going to be posting stream clips and vlogs that we make, which are not in any way intended to be serious. It's all supposed to be just kind of humorous. We are going to stream on Mixer because that's the only way that we can use the camera that we have on my Xbox One, and we're not about to buy a Kinect to do on Twitch. So Mixer, Fredwood Live, and the Twitter account for that is at Fredwood Live. So if you're interested in any of these things, please give us a follow. I really appreciate it.